So let's come to the second concept of this lecture, which is orthogonal matrix. Orthogonal matrix is a square matrix whose column and rows are orthonormal vectors. And if that's the case, then we have this property, which is if you take the matrix and take its transpose and multiply that by m, or equivalently you multiply m by, on the right hand side you have to m transpose, then that will result in an identity matrix. Okay, so the matrix m itself, which has this property, is known as orthogonal matrix, and on the right hand side what we have is an identity matrix that is there. Now if that's the case, we can do something like this, which is I take this m transpose m, okay, and multiply that by m inverse. So if m transpose m is equal to I, so I did that. Since m transpose is multiplied by m inverse, I need to multiply I by the m inverse too. Okay, and what we know is this m inverse is a matrix multiplied by its inverse always results in an identity matrix, right? So if that is known, from there what we can do is we can write this equation, which is m transpose is equal to I m inverse. Why? Because m inverse will be mi, and matrix transpose multiplied by I is equal to matrix transpose that we have. So from this substitution we can see, we can write that the m transpose is equal to m inverse. So we can say, again, we can say that, the matrix M is an orthogonal if its transpose is equal to its inverse. And any matrix that satisfies this property will be known as orthogonal matrix. Okay. So geometrically, what happens? Again, we are talking about numerical concept, but what are the geometric intuitions? Geometrically, the orthogonal matrix is a type of matrix that preserves the dot product after the transformation. Okay, so if you take a vector and transform it V, okay, and you apply that on the same transformation on a vector W, and take the dot product with that, that is going to be equivalent to the dot product of V and W vector. Okay, so the transformation T is orthonormal for all V and W. Essentially, the idea geometrically corresponds to all the rigid motion in which there is no stretching, shrinking, or morphing after the transformation. Okay, and the basis vectors that you have, for example, the unit vector I, unit vector z, are the most common types of the orthogonal vectors that you can use. So you can check all the properties of the basis vectors that is related to orthogonal matrix definition, they will be satisfying them. Okay, there is another name of orthogonal matrix. It is also known as orthonormal matrix. So this orthogonal and orthonormal are essentially synonyms that are typically used to describe the same type of matrix that we have. Okay, so let's take an example. Okay, so here is an example of a transformation matrix that we have, and if you multiply this transformation matrix by x, this will, and let's say the outcome or the output is 0, 2, 8. Okay, so the matrix that we have here, this one will be termed as orthogonal matrix. Why? Because if you take the inverse of it and if you take the transpose of it, the inverse of this matrix will be equal to the transpose of this matrix that is there, and that's why this will be essentially termed as orthogonal matrix. Again, what any matrix is? Any matrix is essentially when you are multiplying that with a vector is a transformation matrix. Okay, so again, let's use this idea, and this let's say we have an unknown vector. Okay, what we are doing when we are multiplying by this transformation matrix, which is orthonormal, then in that case, when the unit vectors are getting transformed, right, you can see that there is no scaling, extending, stretching of the unit vectors in the transformed dimension. They are still exactly the same dimension, and they are still perpendicular to each other. So if you look at previously, here they are one unit, and they are perpendicular, and after transformation, this unit vectors after transformation multiplying with this orthonormal transformation matrix, what happens? They are still perpendicular to each other and they are of one unit length. Okay, so these are the ones which leaves all the basis vector perpendicular to each other and still with the unit length. So any orthogonal matrix will have geometrically this property. When you do the transformation, the unit vector do not get stretched or compressed, and their length do not change, and the length are still unit length. Okay, so this is why, in geometry also, in geometric computation, the orthogonal matrices are known as rotation matrix. What? Why? Because the only thing that they do is they do not stretch or extend a given vector, they only rotate a given vector. So they will only rotate that vector, and that is what is the meaning. Any vector which only rotates and without shrinking or extending that vector is essentially known as orthogonal matrix that we have. Okay, so the example that you can see here and the equations that you see here could be derived by, using these terms of cosine and sine, and you can see these are the ways you can use to define an orthogonal matrix. Okay. So again, if you are focusing on solving a set of linear equation where the matrix multiplied by the unknown vector is equal to known vector, and if the matrix itself is orthogonal matrix. So this is a special case of solving set of linear equation in which once you compose the equation, you arrive at a transformation matrix, and if it turns out that you have a matrix which is orthogonal, and which might not be general case, because if you take any set of linear equation, you might not have a matrix that might be orthogonal. But in case if you have a set of equation and you basically write the matrix vector multiplication equal to vector equation, and if that matrix is orthonormal or orthogonal, then you can compute and solve for those special cases of the linear equation very, very easily using what is known as the dot product theorem. So what you do in this case, you take the dot product between the output vector and all the columns of the transformation matrix will be the same as the dot product between input vector and all the basis vectors. So you can use this idea to essentially solve for this, okay, as the dot products are preserved before and after the transformation. So let's say you have this set of equation, right? This will be, before transformation, this will be unit vectors that we have, and that will be equal to the after transformation with the transformed vector that we have, okay? So here you can see this, right? Maybe in this case, the equation was given by, this was the matrix that was there, that multiplied by xy was equal to 0 and 2, 4. So if you have this specific case where your equation was defined by this matrix, which is 1 root 2 minus 1 root 2, 1 root 2, 1 root 2 multiplied by xy is equal to 0, 2.8. If this was set of linear equation, two variable to linear equation, first thing that I want to note that you will see this is a special case because the matrix that you have in this is orthogonal matrix, right? And if that's the case, if the set of equation, the matrix itself is orthogonal, then you can simplify and solve this problem. So let's see how this could be simplified, and this we can use this special case to quickly solve for this set of linear equation that we have here. So what we will do, this will satisfy this property here. So what we can do from here is before and after transformation, we know this. So from there, what we can do is we can write the solution for x being taking this 2 column vector, multiplying, taking the dot product of this column vector with the dot product with the vector that we have there. If we take the dot product of that, that will essentially give me the solution for x. Similarly, if we take the second column, okay, you will see that second column dot product of that with the known vector that we have will essentially give me the value of y. Okay. So in this special case, when your linear systems equation results in a matrix that is orthogonal, we can take that orthogonal matrix column of each of the orthogonal matrix and multiply that, create a dot product of that with the known vector, and that allows us to solve for the variables that we have in the set of linear equations that we have. Okay, so again, this is a special case, but if you have this special case, then you do not need to use any Cramer's rule or any other width. You can use the simple dot product of the columns of the normal or orthogonal vector with the known vector itself to find out the solutions x, y,